Welcome everyone to this training on testing and commissioning in data centers. Okay. I've tried to keep it as generic as possible and not too deep into technical and cover a breadth of topics. That's the whole idea. It will take about 1 to 1.5 hours depending on how much interaction we'll have. And we'll try to cover the complete journey we will try to cover everything from L1 stage of a data center up to the L5 stage. Obviously, we'll discover if at all someone doesn't know what is the L1 and what is L5, we'll do that. And please feel free to ask any questions as we go. We will have a dedicated Q&A at the end if required. And this training as such has been designed for both construction and testing and commissioning professionals. And we will try to focus on the interdependency of these two disciplines. That's the whole idea. And the idea is at the end, you should be able to understand not just what to do, but why does it matter. My sole purpose would be, so अगर why वाला जो topic है ना, why वाला जो question है, वो answer सबको मिल जाएगी क्यों करना चाहिए. Then I think it is something that we have achieved. So let's start with the agenda to see what we're going to cover today. We have 8 main sections that we are going to be covering. Okay, the section 1, introduction context, I'll just do what is basic commissioning, why does it matter, and so on. Section 2 will be 5 levels of commissioning. What does it entail? It is the longest. It will take the most of the time because everything else will build on these 5 levels. Section 3 is going to be a subset of section 2 in the sense. It will focus on specifically electrical systems testing and some key assets of electrical systems that we'll focus on. Section 4 is designed for, as I mentioned, construction and DNC interdependency. What is the meaning of construction team and DNC teams to work together. And section 5 will focus on short circuit study, arc flash studies. What do they mean? Why are they required? What is their dependencies on commissioning and so on. Section 6, part on as-built documentation. Why is it important? What are the challenges that we face there? How can we overcome them? Section 7 is a small intro on a commissioning platform that we have built in-house, and it tries to solve a lot of the problems that you're going to be seeing in the first 6 sections. That's what it does. And section 8 will be wrap up and Q&A. So, some of the pain points, if I would say, which I would like to understand, how many of you have experienced delays because construction wasn't ready for commissioning? Okay. These are some of the pain points that I'm going to be addressing. How many of you had to redo some work because documentation wasn't updated? I'm sure my BOM colleagues from 63 will have lots of examples on these. So these are some of the issues that we will address today. And throughout the training, I tried to highlight why manual processes create bottlenecks, tracking them instead of tracking issues on paper, spreadsheets, chasing people for status updates, all of these, why it becomes more challenging and what better approaches can we have at the end. So now let's start with the fundamentals as to what exactly is commissioning. That's the first agenda, but just very quickly before that, I think my marketing team has created some slides on my company, which I think most of you know. So I'm not going to go into detail. This is what we do at Efficienergi. We reshape the way electrical networks are managed, and we offer expertise, tech applications to manage overall reliability, safety risk for mission critical facilities. And we've been fortunate to have received quite a few awards in the way. We recently got the Forbes Select 200 award, and we have been doing a lot of sessions, trainings, webinars, etc. across the country, even outside, and on various topics: power quality, electrical safety, reliability, and so on. So that's been something that's been our legacy. That's what we have been doing for a lot of years. And let's get into the meat of the topic without much ado. What is commissioning? I want to ask anyone out there. Can someone help me with a very quick definition of what is commissioning? Commissioning is a quality-focused process for enhancing the delivery of a project. The process focuses on verifying and documenting that the facility and all of its systems are planned, designed, installed, tested, operated, and maintained to meet the owner's project requirements. Now you note that the key phase here is verifying and documenting. Both are equally important. And another important phrase, what you see over here is owner's project requirements. That is very key, right? Because this is not just any standard that commissioning has to adhere to. It has to adhere to what was specified as per the owner's project requirements. Now, commissioning is what? Number one, documentation and validation of design intent. Did we build what was designed? Does it work as intended? That's most important. Second, systematic verification at every project stage, not just at the end or from design through operation. At any different levels, that is necessary. We want to ensure that from design to operation, we are doing that. Then quality assurance to meet owners' requirements. The owner has paid for the specific performance. We jolly well deliver it, right? So these are some of the key things that we need to remember while we are talking about commissioning. And the last is finding issues at the earliest possible stage. So this is crucial, right? Issues which are found in an earlier stage, say a L1 or a L2 stage, they can be much less costly than when they are discovered in a later stage. So we need to find issues as early as possible. Now, what is commissioning not? That I want to also highlight at the same time. It is not, it does not replace the QA/QC of the contractor, right? It is most important, that is to be remembered. It does not replace that because contractors will still own the quality that they have to deliver. Second is, it is not duplication. A lot of times we find that there is a mindset that already we have done the testing. Why do we need to do it again? No, it is not duplication. It is verification that the testing has been done correctly. Third is, it's not something that you add at the end. It is not कि भाई जाके हमने खाली energize कर दिया उसको commissioning बोलते हैं. That's not how it is. It is supposed to be starting at the design stage itself. And last and most importantly, जैसे मैंने पहले भी बोला, it is not just switching on. Commissioning doesn't talk about just switching on. That's a very small fraction of what commissioning comprises of. Okay, so that's what are the key things that I want to remember as far as the previous slide is concerned. Now, why does testing and commissioning matter for data centers? Right. So I want to throw some numbers here, which will give you a story. One, data centers are required. For example, a tier 4 data center certified by uptime is requiring a third digit 99.999% uptime, right? Which translates to only about 5 minutes of downtime throughout the entire year. So that's criticality of what we are looking at. Now, many clients expect this also at the same time. So at a very humongous cost per minute, almost $10,000, I would say, per minute, that data centers can be subjected to in terms of the cost. Even a very small outage can become catastrophic, right? So the idea is that we need to ensure fault tolerance architecture. So that can come from a N+1, 2N, 2N+1. Many different architectures are possible. But the question is, how do you know the backup works? Right? There is a lot of redundancy which is built in the system, but how does anybody prove that the backup systems which have been designed on paper are really going to work when rubber meets the road situation arises? So that's what happens, that you test it. The L4 and L5 stages of a data center commissioning stage, they are exactly designed to test that fault tolerance architecture. And system integration. System integration of a data center isn't just about electrical systems. It is about mechanical, electrical, plumbing, firefighting, ELV, security. All of these systems together come together, the controls, most importantly, come together for performing the system integration test. So, for example, a generator might perfectly work in isolation by itself. But when the generator is coupled with the UPS, will it work properly? Will the UPS at the input side not throw harmonics which are much high magnitude, and not cause the generator to the governor not be able to lock the frequency. That are some of the issues that we are talking about. So we talked about fault tolerance architecture, we talked about system integration, and we talked about tier certification. That is the tier certification of a constructed facility. Unless and until you have a documented commissioning, a TCCF, Uptime Institute TCCF is not made available. And a very important aspect which I want to highlight is that the cost of finding an issue late is, there's a thumb rule, if I would say, an issue found in L1, that is at the factory level, may cost you just notionally say 100 rupees to fix. The same issue found in L5 will cost you at least 100x. It might cost you 1 lakh rupees if that issue is found during the L5 stage. And during operations, even 10x more you can consider. So that is why systematic commissioning matters a whole lot. Now the challenge you can imagine is that how do you track multiple hundreds of tests across dozens of systems and ensure nothing falls through the cracks? Manual tracking creates gaps, and that's what we'll try to look further. Now let's go into the 5 commissioning levels in detail. Okay, what are the different phases of commissioning that we want to that we typically would expect inside a data center? So the first and foremost is the design phase. We call it the L0 phase in sometimes, but it is often the most overlooked. But it is the most critical, right? Because this is where we will review the designs for the commissioning quality. We will develop the commissioning plans and the test procedures. And the adage, it goes, the phrase goes, if you can't test it, then you can't commission it. That you can remember as part of this. So the next is most important. I think most of our time at Listen Lights, I believe, goes in the construction phase. Right from L1, which is the factory testing, before the equipment is shipped to the site. L2, that is your installation verification, QA, QC, etc. Your L3, startup and site acceptance testing. And this is where most of the hands-on work will happen. The meat of the project execution happens over here. Then we go into the acceptance phase. This is when the responsibility transfers from the contractor to the commissioning agency. We will see that in a bit. Here, what we are going to focus on is functional performance testing. Individual systems are going to be tested. In the earlier phases, we are going to focus on individual equipments. Here, we'll focus on individual systems. So each system is tested individually under various conditions over here. And we verify that the system performs as specified in the acceptance, that is the L4 stage. And the last is the operational phase, or the L5 plus phase, I would say, where we go on the IST, or the integrated system testing. We are ensuring that everything is working together as designed. And we are doing a redundancy and failover testing. That's what we're doing. And finally, we hand over to the operations team. Now, the critical part over here is the green tag, which is the color that you see on the construction phase. The word green tag, you will see that I've used the nominal color codes which are used in most of the data centers worldwide. Some cases the color may not be used, some other terminology may be there, but typically I would say 60 to 70% of data centers use this color coding of the tags worldwide. And in this slide, I would say the key takeaway is that the green tag is the one which is a transition between the construction and the acceptance phase. So green tag marks the end of L3, and here the contractor is saying that भाई मैंने installation कर दिया है equipment का, अब आप लोग उसको operation के लिए आगे बढ़ सकते हैं. So CXA जो commissioning agency है, that's the agency which takes the responsibility at this stage. So any issues found after the green tag is not the responsibility of the CXA, but it requires a root cause analysis. That is very important. Okay. So now let's start to dive deeper into each levels. But before that, I want to just get a quick poll from your side. I want to answer. You can either type in the chat box, or you can, people present here can mention. So switchgear has completed startup, load testing and thermal scanning successfully. The GC requests to proceed with functional performance tag testing. What tag status should this equipment have before L4 can begin? Can I have some answers?
Sir is saying green tag Suresh
Okay.
Kalimurthy is saying green tag.
Yeah, I think they are all stalwarts. Suresh and Jaykumar, Jaychandran, you are stalwarts. Yes, definitely the answer is green tag, and it is required to be completed before the L4 functional testing can begin. Okay. So let's dive into now the 5 levels of commissioning. We are going to spend about probably 20-25 minutes on the core of this training. I would say the 5 levels of commissioning, and this foundational knowledge, so that everything else builds upon this. Okay. And for each level, we'll try to cover what happens at the level, who is responsible, right? What documentation is required, the tag coding system, the color system, and common issues and how to avoid. That's what we are going to do. So let's start with an overview of the 5 levels at a glance, at a single glance. So I'll introduce the tagging system first, right? This color-coded tag system is used industry-wide. You have a red for L1, a yellow for L2, a green for L3, a blue for L4, and a white for L5. Right? So L1 is your factory testing, L2 is your installation is complete, ready for pre-startup checks. L3 is your startup is done, and you're ready for your equipment is operating correctly, and you're moving to the functional testing stage, functional testing in the L4 stage, where your systems are verified, not individual equipments, you're going to system verification. And L5 is where the integrated system testing completely happens, where the system is ready for handover. And the key principle here to remember is that you cannot proceed to the next level until the current level is complete and signed off. Right? If अगर ये reality में अगर हम ये करते तो शायद हमारी life में problem बहुत कम होते is what I would say. I think a lot of my colleagues in BOM, Argon, these projects will agree. Unfortunately, the reality doesn't mirror, what we expect in the ideal world. So it is ideally non-negotiable because each level builds on the previous one. That's the whole idea. Now, if you skip L2 checks and go straight to L3 energization, example, I mean, for people who don't know what happens when you skip an L2 and you directly go to L3, you might energize an equipment with loose connections. That's an arc flash which is waiting to happen, right? So that's some of the challenges that you can face if you skip different levels. And the idea is that each level has to be completed and signed out. Issues found late cost 10x more to fix, which is what I told earlier. And again, a tracking challenge here, hundreds of pieces of equipment, each going through 5 levels. Imagine a typical data center site that we work with 200 to 300 equipments in one phase, going through 5 levels. How do you track which equipment is at which level? This is where manual tracking kind of breaks down. So that's just a problem throwing at you to keep in mind. We will look at how we can solve that. Now let's look at each level in detail, starting with L1. So level 1 is your factory acceptance test, called as FAT, and it's a red tag, right? Testing at the manufacturing facility, or it can be verification before you're doing anything at the site, before the equipment ships overall. So this is the first line of defense that we have against any defective equipment, right? That is most important. It is much easier, cheaper to fix, as I mentioned, for issues at the factory than the site. And who typically attends this? That are the key stakeholders. The owner's representative is there. CXA witnesses are there for critical FAT items. For major equipment, that is LLE equipment, we call it, long lead items. Switchgear, transformers, UPSs. Witness testing is very important. What are the examples of what kind of testing might happen during an FAT? For MV switchgear, it can be primary injection, relay calibration, interlock operation, type-out testing. For transformers, it will be ratio tests, winding resistance. We will go into a little bit more detail during the testing phase. But what I want to highlight here is why does L1 matter, right? It matters because we have seen projects where FAT was skipped to save time. The result, defective equipment discovered during an L3 energization. That is catastrophe, right? That is criminal, causing weeks of delay while we are waiting for replacement of parts coming from overseas at times. So that's the key takeaway, I would say. During the FAT, what kind of documentation is required? Each of this testing is in the documentation. Factory test reports, type tests, routine test certificates, calibration certificates, QA/QC sign-offs, photographs, and so on. So there is humongous amount of documentation which is generated, and you might have 50 to 100 FAT reports for every kind of data center stage that you will have to track and organize. So now once the equipment passes FAT and arrives on site, that's when we move on to the L2 stage. And that is the level 2 installation and QAQC verification stage, if you would call that. Now L2 is the barrier between de-energized work and energized work. So that's simply what I would put. You cannot energize any equipment until L2 is complete and yellow tag is issued. This is a safety gate, is what I would call it. It's not just a process step, it's a safety gate. So what happens during L2? One, delivery inspection, where you do checking for shipping damage is there or not, equipment whether it matches the order which has been placed. We're documenting any issues immediately. That's something we're trying to do here. Then there is NETA testing, which is considered a worldwide standard. In India, some of the data center hyperscalers, they mandate NETA level of testing. Some of them do not, but in general, it has it encompasses most of the testing that is required inside a data center. So NETA stands for International Electrical Testing Association. Okay. Now, so during NETA testing, you will go into all the standard acceptance tests for every electrical equipment that is part of the data center. And it typically will include your IR test, contact resistance, high pot, etc. And ideally speaking, out of India, it is mandated to be done by NETA qualified technicians. India may, unfortunately, there is no such agency who is NETA qualified as of yet, as far as I know. Then torque verification. Every connection that you have must be torque to spec. So spec के हिसाब से torquing करना बहुत जरूरी है. Prevents loose connections and which will cause heating or arcing at a later point in time. And it must be documented with the torque values, which is where we at times are lagging. Okay, we do not document each and every torque with the proper torque values, so that there is a possibility that in the future, अगर कोई heating आया, कोई loose connection आया, कोई energization के time पे arcing हुआ, so then there is a fallback for the contractor, for our teams to go and show that at the L1 stage or at the L2 stage, the torquing was done, and this is the proof with the photograph. So common, as far as responsibility is concerned, I want to also highlight that there is different stakeholders here, right? The contractor will do the installation work. The testing agency, like the NETA testing agency, will do the acceptance testing. The commissioning agency, CXA, will do the verification and the witness. And together, both of them, the GC and the CXA, are responsible for signing of the L2 stage. That's the core important part. And some of the common L2 issues that you can come across is that NETA testing is delayed, like the acceptance testing is delayed because the area is not ready. A lot of times we find that we are going for L2, but FOD नहीं हुआ है. जैसे all the cleanliness etc. is not done properly. Yeah, the torque documentation is not available because of that you cannot do L2. IR values are out of specification, so you have IR values which are exceeding the limits, or the favorite one is incomplete as-built drawings, which can cause L2 testing to get delayed, right? And the criteria is listed over there for L2 to be complete, for yellow tag to be applicable. All L2 tests have to be completed. NETA reports approved. Your connection stopped. IR value is acceptable. No open issues, and the area is safe for energization. That's the criteria for getting the yellow tag. Once the yellow tag is issued, we can proceed to L3, that is energization. Before which, again, a small poll. I would want to get your feedback. During L2 verification, the NETA report shows IR of 85 megaohm for an LV switchboard with an acceptance criteria typically is greater than 100 megaohm as per NETA again. Okay, there are different. So what should happen next? Ideally, in your opinion, A, B, C, or D? I'm sure we have had a lot of practical examples where we have gone through this case. Can someone let me know from here?
He's saying the investigation root case and the test doctor.
Corrective action. Okay. Yeah. So that's right. But a lot of times, even A is taken into consideration. At times, teams, try to compromise, saying that it's close enough. Let's go ahead, and we will see during energization करने के time पे देख लेते हैं. No, क्योंकि anyway 2 MOhms तो ऊपर है तो चल जाता है. That's the reference at times you will find. So let's go to now level 3. Right, this is the energization moment. L3 is when the equipment comes to life for the first time. This is exciting, but at the same time risky, because proper L1 and L2, if done, you will avoid surprises over here. Now, what happens over here? Initial energization happens, first power on. So first time power is supplied, we obviously don't want smoke coming out, no sparks coming out, no unusual sounds coming out. Checking the phase rotation, phase sequence, that is very important over there. Then load testing is another important part of this. You have to test all the equipment under load. Generators at 100% load for extended duration, UPSs for the full load, including battery discharge, PDUs for a 4-hour typical load test that you want to do. Then you have thermal scanning during this load test, using the IR cameras, where you identify the hotspots, loose connections, etc. And this is why your load or your torque verification, etc., will matter the most, right? Whatever you've done during the L2 stage. And the green tag significance is arguably that the most important milestone is what I want to tell. It marks, as I mentioned earlier, the boundary between construction and the acceptance phases. The GC is formally declaring that this equipment is now installed correctly and it is operating as designed. So a whole relief can be experienced if we reach this stage without any major issues. And what must be true, or the major milestone for green tag, is that all L1, L2, L3 tests to be completed, all test reports have to be approved, your build issues are resolved, your equipment is operating correctly, and the area, most importantly, is safe and clean. So then equipment downstream can also be given the go ahead for energization. That's the idea. And now, after the green tag, it is important to remember that any issues which are found are acceptance issues. They are not build issues. That's something we need to remember. So let's go to now, L3 has been completed. Let's go to L4, where we are going to test the complete systems, or it's also called as functional performance testing. Now, you're doing the shift from, the major shift here is from equipment, individual equipment, or UPS, or transformer, or DG, to a system. So you are testing in the L3 a UPS unit itself, whereas here you are testing the entire system, that is the UPS, its controls, its alarms, its integration, and everything. And what is the key is failure mode testing. What I mentioned earlier, right? How to ensure that fault tolerant architecture of a data center is working. This is the stage when the actual fault tolerant architecture is subjected to extensive testing. So we deliberately will create failure conditions and verify that the systems are responding accurately. Example, if I would call, say, take a UPS, L4 test for UPS, you will simulate the utility failure, right? AC input failure will simulate. At that time, the UPS should transfer to the battery seamlessly. Most important. Second, you simulate the AC input return, that is utility का return आप simulate करते हो. UPS ने retransfer correctly होना चाहिए. Third is you will reduce the battery voltage, for example, and the low battery alarm should get triggered. Then you will apply an overload. Load shedding sequence should get activated. Then you will simulate an internal fault in the UPS. So the static bypass should engage. So this is what you are typically doing inside an L4 stage for understanding whether each of the systems are behaving as per their specific failure modes, for which they have been designed to operate. And next is that we are going to also be checking the EPMS, BMS, SCADA integration. Right? Each alarm must appear in the monitoring system. That is very important. Your alarm text, your correct severity of the alarm, your correct equipment ID, all of these have to be appearing in the EPMS screens. And this is often the most common place where issues are found. Communication errors are there, point-to-point checks fail over here, your mapping of the points are done wrongly, and so on. Okay. Then you go to the sequence of operations. That's the document which you prepare at this stage, where you are validating that the overall system is operating as per the how it should behave. So it validates how whether the system is operating as per the sequence of operations script which has been defined earlier. So here any deviation must be documented and resolved. Now some common L4 issues which I mentioned, like alarms are not appearing in the EPMS, wrong severity, control sequence is not matching the sequence of operation, communication timeouts are happening. All of these can be common issues that you can expect during the L4. And hence, now what is the blue tag criteria or the L4 criteria? Is that your failure mode to assist alarms are verified, control sequence validated, system is now ready for integration testing. That is your IST or the final stage in the data center testing and commissioning. So once all the systems are blue tagged, we are ready for the final level, that is the IST. Now, IST is in a lot of ways the ultimate test, is what I would say. It's the ultimate test of the entire facility. This is where we are going to prove that the entire data center can survive a real world failure scenario. If you claim, for example, an N+1 redundancy, then whether or not it is really an N+1 redundancy, IST is the time when you are going to prove it. Now, what makes IST different? Right? One is L4 is tested individual systems, whereas IST, all the systems are working together under stress, severe stress. We create here facility-wide situations. What we are doing is we are creating facility-wide failure scenarios over here, as opposed to system-wide failure scenarios that we were doing in the L4 stage. Now, some example IST scenarios that you would come across: utility failure. Right? We will suddenly make all the utility feeds fail simultaneously, so that at the same time all the generators should be kicking in and start to pick up the load. No, the criteria is that not a single IT load should be dropped during this point in time, and the cooling should continue to operate as it is intended to. Maybe for the generator, if I would say generator failure during the utility outage, right? During the utility outage, the generator is, say, all the generators kicked in. Now we will make one generator to trip, and the remaining generators should pick up the load one after the other, and it will thus prove that there is an N+1 redundancy for the generator also. Then cooling failure systems also you will test, where you ensure that the IT load needs to run while you are disabling, say, one cooling unit. All the remaining units should be able to maintain the temperature, and no thermal shutdown can occur during this failure scenario. So, and there is also important aspect is that pre-IST. So pre-IST requirements must be met before the complete IST begins. That is also necessary. For example, all the equipment must be green tagged, as I mentioned. All systems must be blue tagged. So equipments green tagged, systems blue tagged, right? Individual equipments during L3 and individual systems during L4. No open issues from previous stages, and this is where the tracking completion status is very important. And also some cases you might find that there is a 72-hour run also done. I think Microsoft Word, if I know correctly, mandates a 72-hour run where many specifications are requiring this continuous run, where during this period no failures are expected to occur. Any failure which happens during the 72-hour block, it means that you need to restart the clock. You need to restart the clock of 72 hours and start from clock 0. So it again begs the question that it is enormously complex in terms of tracking, because you have 50 to 100 test scenarios. Each scenario involves multiple systems. You are coordinating with multiple stakeholders, and each test is challenging. Real-time tracking, test status, etc., is also essential. So that's some of the challenges. We'll see how we can solve them in section 7. Now we will look at the tagging system very briefly. What does the typical tagging system look like, and how the equipment transition during these levels? I've already spoken to that, but very quickly we'll go through this. This is called a physical tracking system, right? So these are physical markers which you need to attach to every piece of equipment inside the data center, right? So anyone walking through the facility should be able to see, okay, ye L2 ho chuka hai, ye L3 ho chuka hai, L1 complete hai. So that's the whole idea of these physical tags, and it is proven in data centers worldwide. So we mentioned red tag, equipment is completed factory testing. or delivery verification has happened on the site. So the equipment is factory tested and acceptable. Next, the yellow tag, installation complete, all pre-energization checks have been completed. That's the idea for the yellow tag. Next is your green tag, where the equipment has been started and is operating correctly. Your milestone, as I mentioned earlier, the GC is now declaring that I am ready for operation. Means the equipment can be used in the facility. The next comes is your blue tag. In this, the system level testing has been completed, right? All your functional tests have passed, and the system is now ready for integrated testing. And the last is your white tag, which is telling that your IST is now complete. You are ready for handover. Your final tag has been provided, and operations can be now started. Now, the tagging rules, there are some tagging rules that also apply over here. One is that the tags can only go forward. They cannot go backward. Like once you have applied a tag, L2 apply कर दिया और पता चला कि L2 में हमने कुछ miss कर दिया है, you cannot remove the tag and make L1 tag. Then you have to log an issue. Next is tamper evidence seals sometimes need to be provided to prevent unauthorized changes. And tag tampering obviously is a very serious incident. Please don't attempt that. So let's look at the same time who is responsible. Okay, before that, a small poll again, very quickly. If you can tell me, during IST, a utility failure is simulated and all generators start successfully. However, one ATS fails to transfer, causing a partial blackout. Which statement is true?
Sachin sir is saying C. Ajit Kumar sir is saying C.
Yeah, that's right. We need to restart the clock. Even if the generator is started, but since one ATS failed to transfer, small blackout occurred, we have to go back, restart the clock, and start the IST again. At times, there are deviations which are accepted, but typically that's not the case. Any failure during IST requires a resolution and restart of the reliability run period. Now let's go to responsibilities matrix between the GC and the CXA. And why does it matter, right? Because more important is that clear accountability needs to be there so that there's no finger pointing. Because when issues arise, you exactly know who is the person who is responsible, right? So now, first is which levels. We'll walk through each level and who is the responsible person. So at the first level, there is the L1 level. We are talking about factory testing. The GC has to coordinate the factory visits, schedules, witness testing, CXA reviews the test procedures, witnesses critical equipment, FAT, and so on. Both need to verify together that the test results are acceptable. It's not only the CXA's responsibility. Okay. L2 stage, the installation stage, GC does all the physical work, right? Installation, testing, QA, QC, all of that is done by the GC. Whereas the CXA needs to verify that, he needs to ensure that the yellow tag is approved before the energization authorization is given. Then you go to the green tag, that is the L3 stage. Here, the GC has to perform the startup. All the load tests has to be run by the GC, and the CXA has to witness the startup. He has to ensure that the test results are correct, and he has to approve to sign off for the green tag. L4, here, as I mentioned, the responsibility shifts from the GC to the CXA. The CXA is responsible for execution. Okay, and any issues, etc., which are found, GC has to support by operating the equipment or resolving the issues. And both the CXA will document all the results and he will approve the blue tag. And last is your IST. That's your L5. That's your white tag. Here again, GC has to do the work, but CXA leads and verifies the work over here. So here it is not duplication. In a way, it's quality assurance. You're doing quality assurance, and both parties must sign off or the tag for any upgrades, further upgrades. Now let's look at how issues are managed throughout the commissioning. Very quickly, I would like to see how issues are managed during the commissioning stage. Yeah, key point here is that the GC does and the CXA verifies. Remember that. The GC is the doer, the CXA is the verifier. And both has to sign off for level completion. Okay, one more quiz we have here. Relay trip setting is found to be incorrectly programmed during L4 functional testing. Who is responsible for fixing this issue? This is a slightly tricky one. Trip setting incorrect मिला L4 के time पे. नेता जो टेस्टिंग एजेंसी है उसने टेस्ट किया सेकेंडरी इंजेक्शन is they responsible? CXL is discover के are they responsible? Is the GC responsible because it's an installation configuration issue? और the design engineer को क्यों उन्होंने सेटिंग सी स्पेसिफाई उसने की थी तो it is their responsibility. Who is responsible?
Professor is saying C.
Okay.
C.
Yeah.
C.
That's right.
Configuration ही गलत है.
Configuration गलत. So टेस्टिंग एजेंसी का प्रॉब्लम नहीं है, वो डिजाइन वाले का प्रॉब्लम नहीं है, CXA का प्रॉब्लम नहीं है, कॉन्फ़िगरेशन भी गलत किया है. So GC का accountability GC की है. So let's go to the issue management process. So I'll explain. There are three. I mean, there are different ways of classifying it, the issues categories, but I've done it in these ways. The build issues, I will call them, which are the L1 to L3 issues. So these are all found during the construction phase. The GC owns the resolution completely. Anything L1 to L3, the GC owns the resolution completely, and it must be closed before the green tag is achieved. Right? Wrong equipment, installation errors, testing failures, IR values, वगैरह. Then next is the acceptance issues, which are found during L4. So functional testing के time पे जो मिलते हैं issues, those are the acceptance issues. They must, the CXA has to track and document it, but the GC is responsible for fixing it. So alarm not appearing in the EPMS, control sequence wrong है वगैरह. So these are all issues which you can typically expect during the acceptance phase. Then the IST issues. So these are very critical. They affect the whole facility. इसलिए बहुत fast resolution चाहिए होता है. Generator sync नहीं हो रहा है properly, transfer fail हो रहा है. All of that make this a very critical issue and immediate resolution is required. And the last are called as turnover issues, which are post, you can say, at or during or after handover. They are happening. These are tracked for warranty claims. So ideally speaking, ज़्यादा नहीं मिलने चाहिए. If the CX has happened, commissioning has been done well. Okay. But one thing we need to remember here, and where again my experience of working with many GCs is that root cause analysis बहुत ही poor हम लोग करते हैं. If we find an issue and we have to provide an RCA, one, we take a whole lot of time to do the RCA. At the same time, we are not able to dive deep into what has happened because we have not documented it properly, because we have not verified things earlier. इसलिए then the RCA becomes just a lip service or a exercise on paper, and we get smothered by the client for the lack of giving a proper RCA. So, example, you find a loose bus bar connection during the L4 stage, right? It should have been caught in the L2 stage. Torque verification के time पे ही मिल जाना चाहिए था. So RCA investigation के time पे वही होगा कि torque को check किया कि नहीं आपने किसने किया वो torque verification, check किसने किया था, torque apply किसने किया था, documentation किया था कि नहीं, उसका photographs लिया था कि नहीं. So then the corrective action can be to improve the whole torque verification process. But this is where my experience has been that we lack significantly when it comes to doing RCS because our prior diligence is not really there. And next is best practice, I would say, is a daily stand-up meeting, daily push meeting, you call it, buffer meeting, you call it, whatever. Because issues, they do not resolve themselves by themselves, right? Issues don't resolve themselves. Without a daily tracking, multiplication of open issues will happen. And we are witness to that day in, day out. At least 15 to 20, 30 minutes का daily meeting जरूरी है, जिसमें all open issues are to be reviewed, assign, reassign owners करना है, aging track करना है. That is very important. Again, another thing which we don't do. We might do a daily stand-up meeting. We might do reviewing of open issues, but aging नहीं होता है. Issue aging we don't do. So again, it's a pain point. Okay, the spreadsheet problem, I would say. How many of us track issues in spreadsheets today? Most of us, right? We track issues in spreadsheets. Issues will get lost, they will get duplicated, they will get assigned to the wrong person, to the wrong stakeholder, wrong vendor. No real-time visibility will be there into the statuses, and push meetings then become painful finger-pointing meetings. I have been witness to quite a few, so I know it is real. But anyway, that's the idea. So let's move to section 3 now. Specific electrical systems testing. Before which, very quick MCQ again. An MV switchgear which received a green tag 2 weeks ago. Okay. During L4 testing, the CXC discovers that 1-CT ratio is incorrect. It doesn't match the nameplate or the SCCS study. What type of issue this is classified as? Build issue, acceptance issue, IST issue, or a turnover issue?
Chakradhar staff sir is saying B.
Yeah, that's correct. It's an acceptance issue because anything found after the green tag, that is after your L3, is acceptance, even if they are construction related, they are design related, whatever. But resolution has to be undertaken. So we'll go to the next section now, electrical systems testing. For major systems only, I am elaborating over here, not going into each and every small system because we still have to cover quite a lot of topics overall. So let's go into the major MV switchgear testing as the first item. So MV switchgear, what is the criticality? Why MV switchgear is one, it is the entry point for power inside the facility. That's why it is very important. Any failure here will affect everything downstream. So testing has to be very, very thorough, very documented. What are the key tests that need to be undertaken here? One at the L1 factory test. Type test certificate need to be reviewed. Your whether expensive tests have been done on a sample basis or not. Routine tests are performed to the specific limits of the owner. That is important, right? Sometimes the routine tests have to be adhered to, not just based on standards, but based on owner specified requirements also. Mechanical operations of circuit breakers, are they the operating times, are they correct or not? Right. Then the L2 stage, if I talk about during the installation stage, what kind of issues or what kind of tests we need to do. Visual inspection, most important. Damage check. Visual inspection will cover a lot of issues with respect to terminations and the foundations and so on. IR test, like some minimum values need to be checked. For example, for 11 kV and above systems, there are certain 1000 mega ohm is what NETA specifies with respect to IR. Contact resistance, typically certain microohms are the acceptance criteria. CTPT ratio, polarity test for protection and the metering purposes. That's very important. HIPOD test applies. You want to ensure the integrity of the insulation of the switchgear. Then we move on to the L3 startup test, where we're talking about most important is the primary injection test, where you're actually injecting current through the CTs, relays, and verifying the relay responses, or secondary injection, which is you're directly verifying the relay operation to the signals that it receives through the secondary injection testing kits. Then interlock verification, again very important, where you are verifying mechanical, electrical, and various interlocks. EPMS point verifications, point-to-point checks, your timing, trip time, close times, open close times, and all of these for the circuit breakers. All of these are also done over here. And at the L4 stage, that's the functional stage, you are going to be doing protection coordination, that whether your settings are matching the SCCS study or not. Your auto changeover sequences you will apply. If multiple sources are there, whether the ATS is coming into operation or not. All the alarms you are verifying in the EPMS and so on. Okay. So that's the idea of the L for MV switchgear. And here it's important that primary injection testing verifies the complete protection chain from CT relay, trip coil, and so on, whereas secondary injection test only the relay settings at times. So that's the difference between a primary and secondary injection. Going to the next is MV switchgear and transformer testing. So here, what's important is that torque verification, first and foremost. Every bolted connection, small or big, must be torqued to the specification, right, to the spec. This is what is most often skipped or poorly documented, as I mentioned earlier. Because loose connections equal to hotspots equal to fires. Then protection testing, again, trip test on the LV side at various multiples of the rated current. So you have a 4000 ampere breaker, you are applying multiples of that breaker to test it at various multiples, because we want to verify the instantaneous and the time delay characteristics of the LV breakers. And we want to also document the actual trip times that are happening at the various magnitudes of current which are injected. Then thermal scanning, which is your load scanning during the L3 stages, where you're doing the IR camera you are using to indicate the hotspots if any, and ensure you fix any anomalies. And in case of transformers, if I talk about, you have various tests like ratio test, your all the turns, so you're verifying the turns ratio is matching the nameplate or not. Typically, at all tap positions, that's what you will typically do. And tolerance is typically again in the plus or minus 0.5% range that you would expect. Then maybe a heat run test in some cases for the transformer for 4 hours to check the winding temperature, class of insulation. You know, if it's a 115 degrees class of insulation, is it meeting that criteria or not? And the typical acceptance criteria, as per NETA, I would say, as per what you see is for IR, it can be typically greater than 100 megaohm for LV systems. For MV systems, is specifically higher. Okay, you have to refer to NETA standards for this. Contact resistance typically less than 100 micro. Again, it is specific to systems. Bus ducts may have different, your switchgear may have different, and so on. Manufacturer will specify his own contact resistance, or there might be also the fact that unbalance should not be more than say 15% between the 3 phases is also a criteria that is checked at times during contact resistance. Transformer ratio, as I mentioned, within plus or minus 0.5%. Temperature rise within certain limits, and so on. So that's the testing tip. Your documentation point of view, it is important that we capture the baseline. Baseline, this is the stage where you get the opportunity to capture your baseline readings during the commissioning. So it will allow them to become a reference during future maintenance for the customer, right? So doing it properly, documenting it properly, ensuring the tests are done properly allows a proper trending over time, and it provides degradation trends for the customer. Okay, so another MCQ, a dry type transformer shows a temperature rise of 125 degrees during the 4-hour heat run test. Transformer has class F insulation. What is the correct assessment? Except everything class of limits, okay. Even one time. So temperature rise is 125 degrees. The transformer has class of insulation. What is the correct assessment?
Saying C.
C.
Sachin Rajan is saying C.
Yes, that's right. Class F is 150 degrees. So 125 exceeds the limit. So it will fail the class F. Let's move on further to PDU. Why 4 hours? I mean, yeah, there are some of the tests which are there that you can even look at. But why 4 hours is because typically thermal equilibrium, you can expect it to reach within 3 to 4 hours. And a short test, if you do for maybe 1 or 2 hours, it can miss certain issues which can crop up on a longer. And so the temperature typically will continue to rise until it reaches the equilibrium. So that's the reason you typically do a 4-hour load test. Obviously you will want to monitor various things: your temperature, your currents per phases, your voltage stability, how it is. What you want to look for is uneven temperature rise between the phases, if at all. Hotspots when you do the thermal scanning, if it is there, temperature exceeding the limits, right? And inrush current test. That's another important one, which I'm just focusing on, is because when you energize a PDU transformer, there's a brief current spike which happens. And this can be almost 10 to 15 times the nominal current rating of the PDU for a few cycles. So here we need to ensure that the upstream protection doesn't trip, and we need to document the peak rush current, inrush magnitude. Obviously, you will need extremely sensitive power quality meters, PQMs, to capture this for documentation purposes. And the accuracy also needs to be there of these PQ monitoring instruments. Second is metering accuracy. That also is something you want to verify that the PDUs, because they have inbuilt metering, at this point in time, you will also be verifying against the reference meter. Is the PDU metering in line with the reference meters or not? Alarm verification, very important, right? Your all alarms have to appear in your EPMS. Very important. Over temperature, your over current, door open, etc. All of these alarms need to be tested and they need to be appearing inside your EPMS screens. Some common PDU issues which you can expect in our experience, which we have also found: loose bus bar connections that can be found. Metering errors are there. There is a mismatch between calibration is not done properly. Wrong alarm thresholds you can typically find which have been integrated, or communication failures to the EPMS. So that's the typical expectation that you have for a PDU or a RPP testing that you can expect. Now going to the next and most, I would say, another very critical part, which are power cables and earthing systems. What are the reasons, or what are the areas that we need to take into consideration for a testing perspective? Now, why cables fail? What are the reasons why cables fail? That's the first thing I would ask is, one, they can be damaged during installation phase. That's one. Poor termination can be there. You have ingress of water at times. There are manufacturing defects are also found out at some cases. So some of the tests that you will be doing for ensuring the NB-LB cable testing is IR test. That is very common. Here you will be applying DC voltage and measuring the leakage current. Right. So for NV cables, you will typically be testing at 5 kV and typically you will expect more than 1 gigaohm of the IR values. For LV cables, you are testing at 1 kV and typically expecting more than 100 megaohm for LV cables. A low value will indicate insulation damage. Hypot test, you are stressing the insulation or while you're doing the hypot test. So it detects the weaknesses before they fall in service, right? And it must be done before the energization. Thermal scanning is also to be done, right? After the cables are under load. So while you're doing thermal scanning for PDUs or other equipments, the terminations of the cables are also needed to be verified whether there are any poor connections or not. And if there are, you need to fix the connections immediately. Next is the earthing or the grounding system. Again, a very overlooked area of the electrical system, I would say. Typically, the only checks that we take up is your earth pit resistance. But there is much more to earthing systems where we need to pay more attention, because the earth pit resistance is only one part of the overall earthing system checks that we are going to incorporate. One, why does earthing matter? One, because it provides a safety through a fault current path, right? It provides a fault current path and thus provides the safety to human equipment, etc. Protection of the equipment also happens because it limits the voltage during any particular fault. And third is protection from lightning. It dissipates the surge energy. It provides a path to dissipate the surge energy. Now, typical values for earth pit resistance that you will expect, which I've mentioned over here below for both IR and earth resistance. 1 to 5 typically for data centers, I would say. Here there are different standards. IEEE 142 is there, IS 3043 is there, TI 942 is there. Each one of them provides certain different conditions and different ranges. But typically 1 to 5 ohms for a data center for the earth pit resistance is important. Multiple pits in parallel to reduce the total resistance, and testing is necessary using the fall of potential method is ideally what is recommended. Then bonding verification. What is bonding? Every piece of equipment which is there must be bonded to earth. Okay, that's the core. And you need to verify that it has a very low resistance, typically 0.1 ohms. That's the expectation. And your like door frames are there, cable trays are there, structural steel is there. All of these are your bonding equipment which need to be bonded together. And in some cases, you go for step and touch potential also, for ensuring safety during ground faults. This is typically calculated in earth grid design studies, and it might require certain amount of verification testing. Again, we don't apply this a whole lot in Indian data centers a whole lot. It is typically put in the scope of the GIS substation. But what is important is that documentation. Every cable and earth connection needs to be documented. Very important. Cable schedules, termination records, IR values, all of these need to be documented very properly. For a large data center, we know these can run into thousands of data points, but it is the difference between having a smooth commissioning versus fighting helter-skelter whenever there is a small issue which can happen during the later stages of the commissioning. Okay. So that's the typical key equipments which I have covered with respect to testing. Now we'll go to what are the testing equipments that are to be used typically for doing all this testing and what standards you need to adhere to while you are doing this testing. A, okay, A we have, B also we have.
Then it's saying C, Mohit Samir sir is saying A.
Okay.
A, B, C, we have all the options.
All the options, okay. Okay, so I wanted to focus on the most likely cause. The most likely cause is C. Why? Because that secondary injection typically will test only the relay. It will not inject through the entire circuitry. There's a CT, wiring, relay, trip coil breaker. So, वो पूरा testing नहीं हुआ है करके the most likely cause will be all of these were not tested during the secondary injection. That is the most likely cause. Others are also possible, but typically I want to highlight the most likely cause. Okay, so now the next section which I wanted to take is the interdependency of construction and testing and commissioning. Right, very critical section. That's why I've highlighted it in red. This is where most project delays originate, in my opinion. I don't know, Monty sir, if he's there, he will be most interested in this topic. This is where the handoff between construction and TNC is often poorly managed. So, how many of you have experienced delays because construction wasn't ready when TNC arrived? Just say yes in the chat box. Or documentation was missing or incomplete. या तो issues were pushed from construction to commissioning. So these are the problems that we are going to address. I hope there are some yeses in the screen, in the chat, where people have faced issues that construction ready nahi hai, TNC karo, QA/QC हुआ नहीं है पूरा, cleanliness नहीं है, safety नहीं है, documentation as built नहीं है, वगैरह वगैरह. So that these are the problems that we are going to address today. And my key message that I want to pass on here, okay, before I dive into this, is that construction and testing and commissioning are not sequential. They overlap with each other, and poor coordination in this overlap causes cascading delays. That's the message I want to do. We'll look at prerequisites, we'll look at handover challenges and best practices. Okay. So the construction DNC handoff challenge. पहले हम लोग कंस्ट्रक्शन करते हैं, फोकस ऑन इंस्टॉलेशन होता है, कंप्लीशन परसेंटेज के हिसाब से मेजर करते हैं हम कितना परसेंट कंप्लीशन हुआ. दिस इज अ कंस्ट्रक्शन माइंडसेट. ओके, हैंडओवर हमने हाँ मोटा मोटा हैंडओवर हमने कर दिया है, मोटा मोटा हो चुका है, इनफ हमने कर दिया है, वी आर 95% कंप्लीट. दैट्स द माइंडसेट, राइट. पंच लिस्ट थोड़े बहुत इश्यूज पेंडिंग है, बाकी अब टेस्टिंग चालू करो तब तक सॉल्व हो जाएगा. नाउ this is where the gap occurs with respect to the TNC mindset. So the TNC का mindset क्या होता है कि 100% ready है कि नहीं टेस्टिंग के लिए, मेरे को complete documentation चाहिए, as built documentation complete चाहिए. Any open issue means a blocker for me. मुझे all prerequisites clear चाहिए. That is the TNC mindset. So this is where the gap starts occurring, right? Here I would say nobody is wrong. In a way, nobody is wrong because both of the teams are using different criteria. They are using different parameters to measure their completion criteria. So the consequences at times happens is that construction bolega ki done, TNC bolega not done. So what are the consequences? The TNC team arrives to find the area cleanup nahi hai, ya safety concerns unresolved hai, documentation completed nahi hai, equipment is not ready for testing. Right, we have found issues during TNC, loose connections मिलते हैं, या wrong equipment install किया हुआ है, पूरा labeling पूरा गलत किया हुआ है, documentation installation को match नहीं करता है. These are all the examples I have seen. I have seen TNC teams wait for weeks on end for a single document to find for before analysis. That are the kind of delays we have seen. So let's look at the prerequisites which are necessary before each level. So for before L2, what we need is a prerequisite. Very important. Installation 100% complete as per the issue for construction drawings. That is number one. Second is your testing. Sara complete hona zaruri hai before you go for the energization. SCCA study, which we'll speak about in a bit, short circuit and coordination study, that has to be approved, right? Area has to be clean for electrical work. आपका लॉकआउट टैगआउट वगैरह प्रोसीजर सारे इन प्लेस होने चाहिए, नो डेब्रीज, अप्रोप्रिएट पीपी वगैरह आपके पास अवेलेबल होना चाहिए, इमरजेंसी एग्जिट्स क्लियर होने चाहिए, फर्स्ट एड फायर एक्सटिंग्विशर्स शुड बी इन प्लेस, upstream power should be available. That is also another important criteria. Then before L3 is concerned, as far as L3 is concerned, yellow tag obviously हो जाना चाहिए, आपका formal sign up हो जाना चाहिए कि L2 आपका complete है, EPMS should be connected. That is also another necessity, right? And monitoring must be in place. So all the monitoring should be in place. Alarms must be visible before you go to L3. And lastly, before L5, when I talk about most comprehensive stage, right? सारे equipment green tag आपको चाहिए, systems आपके blue tag which I spoke earlier. Every checklist item by item you have to go through. Your capacity is available to test. मतलब आपके load banks should be in place to test the entire megawatt of the data center capacity that you want to test it for. अगर anything open है तो आगे का stage cross नहीं होगा. That is the whole idea. So before each level of transition, hold a formal review to verify all prerequisites are met. No exceptions. No, we will fix it later. We should not be going into. Okay. So what are the common construction gaps? Very quickly. Okay. Documentation is number one. The first and most important. Construction happens, drawings don't get updated. TNC team के पास drawing होती है, they don't match reality, causes confusion and safety risks. Next is installation gaps. Terminations almost done. मतलब रिपोर्ट सबमिट होते नहीं है उसके, टेस्टिंग किया लेकिन टेस्ट रिपोर्ट सबमिट नहीं किए, रिजल्ट्स को वेरीफाई कर नहीं सकते हो टेस्टिंग के बगैर, मतलब डॉक्यूमेंटेशन के बगैर, तो इट ब्लॉक्स द येलो टैग अप्रूवल. देन इंस्टॉलेशन के टाइम पे या तो कोऑर्डिनेशन के टाइम पे यू विल फाइंड दैट एससीसी स्टडी आपका हुआ नहीं है और यूटिलिटी कनेक्शन डिले हो गया फ्रॉम द क्लाइंट साइड एट टाइम्स, परमिट्स आपके मिले नहीं हुए है, सो द एंटायर delays happened, third party inspections are pending. So all of these are different blockers that cause TNC to not perform optimally because of construction related gaps. So each gap can delay the TNC by days or weeks. Multiple gaps compound. Common thread, lack of real time visibility into what's complete and what's outstanding. This is very crucial, right? Because information क्या है ना silo में होता है. There is no shared tracking system available. It's a reliance on meetings and emails for status. कोई early warning नहीं है, कोई blocker नहीं है, मतलब कोई potential blocker का early warning मिलता नहीं है. तो solution preview अगर मैं बोलूँ, if I preview a solution for this, what if both the teams could see the same dashboard? What if prerequisites were automatically tracked? And what if issues were visible to everyone in real time? That's something if can happen. It can be utopia, right? It is for me utopia. Okay, so coming up, I think the second last MCQ of the day, a little more in-depth one. The SCCA study was completed 3 months ago based on design drawings. Equipment is now installed with the following field changes. Cable length 15% longer than design. One transformer tab changed from the nominal. 2 changes were observed in the field. Which change requires a study revision or not? Okay. And why would you say that?
Then the 15% length also increased, and then the tab also changed. So you need to
Okay. So I think interest of time will move forward. Yes, it is both the changes will require revision. However small a change it is. अगर केबल लेंथ समझो RMU से ट्रांसफार्मर का लेंथ 15 मीटर की जगह पे 20 मीटर हो गया, then there will be a change in the SCCA study required, and that You can imagine the kind of delays it can cause to the charging of the R&D or the transformer. So that's why it's very important for ensuring that we do the design changes as early as possible. So what are some of the best practices that I would want for a proper coordination between the construction teams and the testing and commissioning teams? First and foremost, most important, I want early engagement, right? The TNC should not be an afterthought. Involve the CX agency from the design phase. Very important. Review the commissioning ability of the design. That's what I would say. Develop the scripts, test procedures in parallel with construction. I have found cases where टेस्ट स्क्रिप्ट्स कोई बना रहा है साइडों में बैठ के उसके अंदर डाल दिया कि 5000 एम्पियर का इंजेक्शन टेस्टिंग करना है और कंस्ट्रक्शन के टाइम पे इंस्टॉलेशन टीम्स को पता ही नहीं है, पॉसिबिलिटी नहीं है करने, आप उसको डालोगे टेस्ट स्क्रिप्ट के अंदर एंड देन योर कमिशनिंग विल गेट डिलेड बिकॉज वो कर ही नहीं पाओगे, फिजिकली पॉसिबल नहीं, तो यू गो थ्रू द होल लॉट ऑफ डिलेज एंड आइटरेशंस. Second is joint planning is what I would say. Construction and TNC schedules have to be integrated. Weekly coordination meetings with both the teams, rolling 4-week look ahead, I would say. I know it's very important. You can have that. You can identify much earlier. Then clear prerequisites, which I spoke about earlier. Remove the ambiguity from the ready definition. Ready ka definition मतलब checklist के through ही होना चाहिए. There should be a checklist for every level transition, right? You gate the reviews. मतलब every sign off should be gated. It should be through a reviews only, no exceptions. Then real time tracking. Both teams have to see the same information. That again is very critical. Equipment status visible at a glance. Issues tracked centrally, not in personal spreadsheets. Very important. Then daily push meetings. If we can have an idea, 15 to 30-minute push meetings जहाँ पे blockers review करो, single point of contact रखो, वगैरह. Critical phases के टाइम पे रोज मिलो. Then energization is another critical criteria. Single point contact रखना है for energization. He has authority to grant or deny energization. That helps to prevent any conflicts from energization related challenges. So this is, success factor, if I would say, is that these are difficult to sustain with manual tools, right? These are proven practices, effective practices, but hard to sustain with manual tools. The best projects will use integrated software tools for real-time tracking and coordination. Your spreadsheets can get outdated, meetings can become very painful, people can revert to old habits. But if you have a single visibility tool which provides everything and anything, then what if they were built into a workflow? What if tracking was automatic? What if reports were generated on demand? Right? So that's the idea. Now let's look at the next section, which is your short circuit and coordination studies. Another very, very important part of commissioning, and in my opinion, one of the biggest blockers at multiple stages, which almost every site typically experiences. So, short circuit analysis. What is short circuit analysis? Right. One, it models the electrical system, calculates the fault current at every point in the electrical system, determines if the equipment can withstand the fault or not. For example, if the fault current is 50 kA, the equipment must be rated for more than 50 kA. That's as simple as that. That's the short circuit analysis. Then next is protective device coordination. So here we are trying to set the trip times of every protective device in milliseconds, seconds, whatever that be, in different zones. So here you are trying to ensure selective coordination between the entire path that is available, right from the MV all the way to the transformer, secondary to the PDUs, to the rack level. So the upstream device should fail or trip only if the downstream doesn't trip. That's the whole idea. And it prevents any unnecessary outages. Then third is arc-flash analysis. So here you are trying to calculate the incident energy which will be imposed on the equipment when the arc occurs or a fault occurs, and how to keep the incident energy minimum by proper coordination. And whatever incident energy or whatever PP are required to operate that panel, those labels are generated. So it's more of a life safety issue. Then why do these things matter? Why do SCCS studies matter very importantly? Okay, one, underrated equipment can explode during faults. You have an equipment which is of a lower fault rating and it has a fault rating at that bus level is higher than the equipment, it can literally burst and explode, right? It can black out the entire facility, but if a proper coordination is done, it limits the outage to the affected area only. It will allow the limited area to be get affected. Then next is worker safety. Arc flash can cause severe burns. Smallest of arc flash energy of only 2 calories per centimeter square can cause a second-degree burn, which is equivalent to a cigarette burn on the skin of a person. So that's why it's very important that arc flash injuries are prevented by doing a proper arc flash analysis much beforehand. NFPA obviously is one standard which requires this. IEEE 1584 is another standard that requires this. What is important here is that there is a timeline track that I want to talk about here, which I spoke earlier also. But one of the most common project delays. The equipment is installed, it is ready to energize, but SCCS is not approved yet. We cannot program the relay settings without the SCCS. As a result, weeks of delay happen. What is the best practice? As opposed to this, you have to start SCCS during the design stage. That is necessary and mandatory, I would say. During the design phase, you have to start, but you have to issue some preliminary studies. What happens today, unfortunately, the SCCS study is such a understood subject that people want it in toto, in a completion at the first stage itself. That is not possible because your designs are evolving, your equipment's ratings are changing. Your your breaker makes and models are changing when they are coming at site as opposed to what they were during the design stage. So you need to go through multiple iterations and those need to be factored in during the initial stage itself when you are finalizing the SCCS study with whichever vendor you are going to be conducting. That there will be minimum required 5 iterations. Those iterations have to be costed accordingly. They have to be priced accordingly so that there is no conflict at a later point in time when there are changes in drawing, changes in specifications and so on. So that's what is more concerning typically that we have observed from an SCCS perspective. Next, let's look at arc flash analysis and labeling. So what is important in arc flash is different categories of arc flash are there. These categories are based on incident energy. So you will have a category 1, for example, which is 4 calories per centimeter square, right? So these categories are based on higher the energy, higher is the potential for severe injury. So higher the category, more protective equipment you will be requiring, as you see over here. So starting from a basic arc-rated clothing to a multi-layer arc flash suit would be the progression in terms of the PPE that you would require to have with you while you are performing energized work on any equipment. And every piece of equipment must be labeled as long as it is typically a 3-phase 440, 400 volt and rated equipment and above. The label must show the incident energy. It should show the arc flash boundary distance. It should show the working distance. Equipment identification should be there, and the identification should match the drawings. Again, very important. When the study has been performed needs to be there. The upstream protective device also needs to be there in the arc flash label. Okay, and during the commissioning verification, during L2, L3, typically you need to verify that the labels are installed, labels are matching the study. This is common error. Okay, labels have become old or obsolete. Breaker relay settings, they match the study assumptions, and if the settings do not match, then the energy may be different. That also is a possibility that you need to remember. And PPE readiness is very important. So all the appropriate PPE as per the labels need to be available at that area of operation. The personnel must be trained and they're ensuring that this is a safety gate. And most common issues is what we have seen in these cases is labels are not installed before analyzation, or labels are not final. They are from the preliminary study, or the settings have changed, but the arc flash labels have not changed, or the PP is not available at site. These are the common issues that we typically observe. So our last MCQ of the evening. Panel has an arc flash label showing 6.5 calories per centimeter square incident energy. A technician needs to rack out a breaker. What is the minimum PPE category required? This is fairly easy, I would say. Yeah. Cat 2, typically you require 8 calories per centimeter square. It should be rated above the incident energy, whatever is there on the label. The next highest category should be available. So I think we are reaching time is going to be short, so I'll wrap up. As-built documentation, I'm not going to do a whole lot. It's very simple. Why as-builts are critical, I think we all know. SCCS, I think that's the only one point I want to stress. That SCCS settings are tremendously dependent on as-built drawings, and the more there are iterations or changes in the as-built drawings, the more iteration there will be there in the SCCS settings. So a typical scenario is what you can see over here. You issue the setting based on design drawings, then there will be equipment which are installed with changes, study doesn't match the installation, revision requested, 2 weeks delay, more changes found, another revision, and so on. So typical cost escalation increases because of this, which we have experienced at multiple sites. Okay. So that's the message I wanted to give over here. And to reduce as-built iterations as a best practice for accurate documentation, one is do concurrent updates. Parallel. Do not wait until the project ends to update the as-builts. I think it's already started. Single source of truth, right? One master drawing set, everyone looks at the same version. That is very important. Early SCCS engagement, I already spoke about, ensure that we are doing engagement faster and earlier. Ensure that we are having a field verification. Whatever we are submitting, verify on the field. Before submitting SCCS data, verify on the field. Read the equipment nameplates and so on. And ensure that we are managing control. Changing the change control is managed. Every deviation, etc. is managed. So again, these practices are well known, I know, but they are hard to sustain manually. So again, my open question: what if as-built data was captured automatically? What if every test recorded equipment data? What if changes were flagged in real time? Right. So that's the answer. If at all we get, that would be really great. So I think I'm just summarizing now the key challenges that we discussed so far. Okay. First, tracking equipment statuses. That's what we said. Tracking hundreds of items progressing from L1 to L5, which are ready, which are blocked. What is blocking IST? Manual tracking cannot keep up with this. Documentation control. Are test reports scattered across multiple folders and emails? Is there multiple versions of as-builts? No single source of truth. Reporting burden. Status reports or testing reports. They take a lot of times to come. By the time the report is done, is the data is already stale, right? Leadership doesn't have real-time visibility. Then we're talking about issue management. Issues are logged in different systems. Construction has its own list. TNC has their own list. No shared visibility. Push meetings become data reconciliation exercises. Then we're talking about coordination gaps. Construction and TNC using different criteria. Prerequisites not clearly defined or tracked. Handoffs are failing repeatedly. And last but not the least, SCCS iterations. So what is the common thread between all of these? What do these challenges have in common? Is what I feel is that they are all rooted in manual processes. Spreadsheets, emails, paper forms, and they're not designed for complexity. So what if there was a better way? What would solve these challenges? One is real-time tracking, right? Where you can imagine a dashboard showing every equipment item, color coded by status, etc. A unified platform, automated workflows. I would say where the system checks prerequisites automatically. You don't need to. You cannot request an L3 until L2 is complete, right? That is possible. Mobile access. If you can have everybody has on their mobile phones, data, etc. Everything is available. A unified platform, which is one system for everything. Issues, documents, equipment status, everything is available over there. No more spreadsheet reconciliation required. On-demand reports, if you can click a button to get a report on demand, on periodicity, whenever on a schedule that you require. Daily, weekly, custom reports, and so on. integration ready. It connects to your existing tools. For example, say it connects to Procore, connects to Compass, or any other software that you have, right? Document management integration and so on. So the technology for all of this exists, and it has matured significantly in the current years. That's what one small area I wanted to speak about. We talked about these challenges: the tracking complexity, the coordination gaps, documentation burden, and what an ideal solution would look like. So we have been working on this, exactly something like this over the past many years and months, where our own teams have done that. So let me just show what we have built very quickly. This is Secure CXP. That's our digital data center commissioning platform, where we are using it to track all of these issues which I spoke about earlier. And we're doing a big shift from Excel-driven chaos, I would say, to a predictable data-driven commissioning. And some of the key features that CXP brings in is planning and scheduling, intelligent activity planning with dependencies, auto-generated schedules, dynamic replanning, complete equipment management. So equipment registry is available completely with location-based, where it is, where are they organized and so on, and dependencies mapping also. So you also know which equipment has a dependency and before which you cannot proceed to the next stage. Testing and commissioning. So you can go as granular as an IR test result inside the system. Real-time activity tracking is there, results recording and commenting. Issue tracker are already inbuilt, real-time issue logging with severity, etc. Collaborative resolution with audit trails and reporting, most importantly. Progress dashboards are there, KPIs are there, custom reports, on-demand reports, export capabilities for documentation. All of this is inbuilt. So the ROI we have found is very immediate. Cost of 1 day delay, typically can be crores for a typical data center. From a hyperscaler perspective, from a co-location player perspective. And we find that happens because of coordination gaps. So that cost can be recovered almost in 1 day is what we find. And these are some of the numbers that we have actually validated by using CXP at some of our sites. More than 70% faster coordination, 30% faster report review and closure, 25% faster test completion, and 80% reduction in delays, firefighting, and rework. So I'm not going into too much detail. We can discuss that if at all anybody is interested to go in more detail. And these are more main features: web application, there is a mobile application, and there is an offline capability. So it works together. All of these three work together for anyone who is really interested to leverage it. So coming back, I think this is almost my last slide. Key takeaways from the entire session. L1 to L5 is a progression, right? You cannot skip levels. Every level builds upon the previous level. Sign-offs, typically consider them as gates, entry gates. They are not suggestions. Then green tag is very critical. It defines your transition from construction to acceptance. The GC declares ready for operation. That's your green tag. And your issues will become acceptance issues after this point in time. Then construction and TNC must align. That is very, very important. If we need to succeed as a team, this is our section 4 where I spoke about this. Clear prerequisites, no ambiguity, joint planning, same schedule, real-time tracking, shared visibility, right? Then documentation is very important. That's what will drive the success of the overall project. Your SCCS settings, iterations, it will reduce, saving time and money. Concurrent updates will be there, not in batches. Manual process breakdown. Spreadsheets are not enough. Email is not a tracking system. Modern commissioning software exists, and you have the ROI, which is already there. So my last question for the audience would be, which of these resonates most with respect to your current challenges? Or what would make the biggest difference in your projects? And with this, I open the floor to questions. Would really love to hear your thoughts, and hopefully this was worth your time. And thank you so much for being so patient and being here with me. I may have gone a little fast, but really appreciate your time. So what does resonate the most, if I were to ask, as far as the current challenge is concerned? Your experience, any challenge that you typically face as QA/QC?
In that clean time.
Getting time, getting the green time. Audience, anyone? Please kindly, you can please unmute, ask any questions also. That's also, please go ahead.
Hello.
Yes, sir.
Sir, I have a question. I want to ask why we use AC hypot kit for testing a bus bar.
Why we use?
Yes, we can use why we can use DC hypot kit.
See, why you cannot, sorry, why you use the AC hypot kit you're saying, right?
Yes.
So see, typically your DC is always typically more destructive in a way, I would say. Okay, when you're especially doing hypot, because that's a stress test of your insulation. In your real life situation, real life condition, you are not going to be subjecting your bus ducts through a DC component. It is to be having an alternating frequency, right? So ideally speaking, you want to apply AC signals while you are testing the insulation healthiness. That's the reason you do that. And a more higher DC voltage, if you apply during a hypot, it can become destructive for the bus duct. So that's one of the reasons that you do not want to apply a very high DC hypot voltage.
But we perform the DC voltage in cable.
Yes, but it is at a very nominal IR that you're doing. In cables, you do DC hypot for high voltage cables also, yes. The limitation is your size of the kit that comes into picture. Your kit becomes very bulky if you have to apply at the 50 Hz frequency AC hypot voltage. That is the reason you go for a very low frequency that is at 0.2 Hz AC hypot test, which is a more preferred test for doing stress testing of the insulation of cables.
Okay. Thank you, sir.
Yeah.